Hey everybody, I'm Simon, this is Antiverso, and today we're gonna talk about Bayes Theorem and the Naive Bayes Classifier. And you can probably see the Bayes Theorem formula. So we're gonna explain what it is, how it's working, and we're gonna try and make here some probabilities and likelihoods and all of these things that we can think about. We're gonna make them a bit simpler, and step by step we're gonna try and explain how it works and why is it so good. Well, the Naive Bayes Classifier is first of all supervised machine learning algorithm, right? We have some data which is labeled, right, with input data which we call features, and output data which are the labels, so the true real answers, right? And we input it into some kind of machine learning algorithm, and we are trying to synthesize, we call it a model, or simpler said, some kind of rule that later we can apply new data into it and we can classify this data. For example, we can have training data or training set, which is pictures of cats and dogs, and we can input that into a machine learning algorithm which will output a model, or also we call it classifier, which later we can just input one by one different random pictures and it can tell us, is this a cat, is it a dog, and so on. This is what we're trying to do. Obviously, the type of machine learning algorithm you want to use depends on the data you have and what you're trying to achieve. And the Naive Bayes Classifier is very good for simple data, because it's very simple, but it is quite robust and reliable, which makes it actually very powerful, because it makes some assumptions, but even if those assumptions are violated to a degree, it still works. So let's get into it. I'm gonna use an article which is written by Sebastian Rashka, and you can see the link. You can go out there and read, and the other things he has written, he's amazing. And I'm gonna try and explain some of the big ideas and kind of overview stuff. So the Naive Bayes Classifier, it is very good for distinguishing linear data, and here we can see A and B, and in A the data could be classified with a straight line, right? While in B this cannot happen, which means that we can use the Bayes classifier for A, but we can't really use it for B, or we could try, but probably the results will not be that good. What the Bayes classifier allows us to do is to take some kind of prior knowledge and, as I said, divide this into some kind of measure of how probable is a sample to be part of different classes. And then when we compare the probability for this sample to be from different classes, we can actually pick the highest one and say, okay, we just classified this sample. And so this is the Bayes Theorem formula which we saw here, right? But this is kind of explained into words, right? So here we have the posterior probability. What Bayes Theorem allows us, this measure that I was talking about, it allows us to find out what the posterior probability of the different samples is. And here, in a more mathematical notation, it's PA/B. What the posterior probability represents is how probable is a certain class to be observed based on the sample we have, which is exactly what we want to know, right? This means that we can say, okay, this sample is from this class. This is the notation of the class, right? This is the notation of the sample or input features, right? Here we have A, B, and what's the probability that having this feature, or this sample, we have a certain class. So what's this equal to, right? This is what we are trying to find out. It is equal to the conditional probability multiplied by prior probability over evidence. And you say, oh, hold up, I don't know what these things are. Let's look at them one by one, okay? Conditional probability is the reverse thing. Here we have PBA, right? And here we have the sample notation, or the features notation, and the class notation, which means that, okay, what's the probability having certain class to observe this particular pattern, features, sample. And the way we find this out is through the maximum likelihood. And what it is, right, is just a way that we can calculate the conditional probability. The way we do that is for a pattern, right? This is a pattern, which means that, this is basically a vector, right? It has feature 1, it has feature 2, it has, n number of features. And the way we can find the probability of this particular pattern to be observed into a certain class is by multiplying the probabilities of each of its features to be observed into a certain class. And if that sounds a bit convoluted, let me explain it. For example, me and my sister picked 500 red apples today, okay? I picked half of them, which means 250, and my sister picked also 250, okay? Half of the apples I picked them in the morning, okay? And the other half, I picked them into the afternoon. So this is our data set. And what I'm asking is, what is the probability of observing the pattern of a red apple that is picked by me in the morning, right? Having in mind all of the red apples. And what I can do is, okay, red apple picked by me in the morning, right? So the probability of an apple to be picked by me is 1/2, right? It's 0.5. Then the probability of an apple picked by me, that's red apple, right, in the morning is also 1/2, right? Because of all the apples that I picked half of them in the morning, which means that 0.5 multiplied by 0.5 results in 1/4 or 0.25, which means that the probability of observing the set pattern is 25% having all red apples. And if we think about it, that is exactly true, right? We have 500 apples, I picked half of them, which is 250, and I picked half of them in the morning, which is 125. 125 divided by 500 is exactly 25%. So now we know what maximum likelihood is. It's using the different features, multiplying their probabilities in order to find the class-conditional probability of a set pattern. Now, why we can do this, right? There should be a theory behind it. Well, the theory is that in the naive Bayes, why it's called naive, right? Because we assume that different data samples, right, different input features are IID, or what it stands for is independent and identically distributed. What independent means? It means that the occurrence of one feature does not affect the occurrence of another feature, right? And the classic example of this is tossing a coin, right? Getting a heads, on the first row does not affect in any way, the second row and what you get in the second row, right? It is independent. What is not independent is, let's say, the probability of watching episode 2 of Westworld when you have watched episode 1, right? Obviously, if you have watched episode 1, there is much greater probability that you watch episode 2, so they're not independent, right? I mean, having in mind how great the show is. So, what is identically distributed? This means that we assume that the points form a normal distribution. As you can see, a normal distribution means that the points are evenly distributed into the data space around their most probable point, which is the highest point, right? Which means that they're not skewed in one direction or another direction, affected by some outside thing that is telling, okay, here we have more, here we have less. Now, in general, in the real life, most of the time these two conditions are violated up to a point, right? There is very little real data or in real life situations when everything is independent and it is, it's not affected by anything outside, so it's, identically distributed. As I said, the Bayes classifier turns out to be very robust, and, even if those are violated up to a degree, Bayes still performs very, very well. Now, the second term of the formula is prior probability. So what's prior probability? As the name suggests, it is some kind of knowledge that we have from the beginning, right? It's a prior knowledge. So what's that prior knowledge? Okay, this is the prior knowledge of what's the probability of observing exactly this class we're talking about. And here it's outlined, right? This is the prior probability of the class, and what it is the number of samples from the class over all of the samples, right? Let's see, my and my sister picked not only red apples but also picked yellow apples, okay? And we picked 500 red apples and 500 yellow apples, total 1000 apples. This means that the prior probability of red apples, the class red apples, is 500 over 1000, which is 1/2 of 50%. Now I want to read that because it's very important. If the prior probabilities are following a uniform distribution. What does uniform distribution mean? It means that basically they have the same probability, okay? The posterior probability, what we're trying to find, will be entirely determined by the class conditional probabilities, okay? What we looked at up there and we found through the maximum likelihood, right? And the evidence term. And since the evidence term is a constant, why it's a constant? Because we have one evidence, right? We have one training set which we are training our model on, right? So it's a constant, which means that we can remove it. The decision rule will entirely depend on the class conditional probability, similar to a frequency approach and maximum likelihood estimate. What this is trying to say that we have one evidence, which means that actually when we are doing our calculations, we can remove the evidence and forget about it because it's the same for all of our points, right? Then the prior probabilities, if they're uniform distribution, means they're the same, right? So why would we, multiply all of our different points, with the same multiple? It's senseless. So we can remove this, which means that we are left only with posterior probability equal to conditional probability. What that means is that the probability of a certain pattern to be part of a class will be only dependable on the probability of this pattern to be observed in this class, which makes sense, right? If the probability, of red apples being picked by me is the highest and we have a red apple, then probably it will be picked by me and so on. But this is only when the prior probabilities are the same. And here in this picture, we can see the representation of what I just said, right? We have normal distributions. We assume they're independent, right? And this is class 1, the blue one, and class 2, the green one. And we can see that if the prior probabilities of both of them are the same, which means that there is 50% chance prior probability of a sample to be from class 1 and a 50% chance a sample to be from class 2, the decision boundary, which is this one, is exactly in the middle. It is where the two distributions meet, right? And it makes sense because there's literally no probability from a sample to be from class 2 if it's, let's say, around 4, and there is literally no probability for a feature to be from class 1 if it's around 10. But in the moment that the prior probability shifts, then the decision boundary also shifts. And here we can see if the prior probability of class 1 is more than class 2, which in my example with the apples would be if, let's say, we picked 600 red apples and only 400 yellow apples, then obviously the probability of different features to be from class 1 will be bigger, and then the decision boundary will come here, which means that there will be much bigger data space for class 1 than from class 2. Now, the last thing that we need to talk about is the evidence, right? Even though that I kind of gave you a spoiler that we can remove it. But why is that? Because the evidence is the probability of encountering or observing a particular pattern independent from the class label. So how can we find that? It is quite simple actually, right? We have the conditional probability. What's the probability of this pattern to be part of this class multiplied by the probability of observing this class, plus what's the probability of this pattern not being in this class multiplied by the probability of not this class. And as we said, what it turns out is just a scalar, right? It does not actually affect our decision boundary or overall posterior proportion of posterior probabilities. So this is our overall formula, right? We can calculate these things and we get a posterior probability. What the classifier does is it tries to maximize this posterior probability, and wherever it finds the maximum posterior probability, it makes a decision that this particular pattern is part of this particular class. I want to finish with a simple example which is amazingly explained by this article, and I'll just go through it and try to explain it even better. So here we have what is called multinominal naive Bayes, which means that we have a few different classes, and each of these classes has different features, right? For example, here we have two classes, we have plus and minus, and each of these classes has two features, right? It has a shape and a color. So if you have to explain what multinominal naive Bayes or classifier is, you can just remember this example. There is nothing harder and more complicated than this, only the names are complicated. So we have this training set. As I said, the first feature is color, which could be blue, green, red, yellow, and the second feature is shape, which could be circle or square, right? And we have the two different classes, plus and minus. And we have a new feature, which is a blue square, and we can kind of cheat that it's of class plus, but we'll pretend that we don't know what the class is and we want to find it out, okay? So in order to use Bayes theorem and the naive Bayes classifier, in order to classify it as a plus, we know what we need to do, right? We need to say that the posterior probability of having this pattern, which is blue square, to be part of class plus is bigger than the posterior probability of the same pattern to be from class minus. So what we can do about this? Well, we know already the formula, right? Since, as we said, we have the assumptions that the samples are independent and identically distributed, we can use maximum likelihood in order to find the probabilities. We have 12 samples, okay, 7 of them are pluses, which means that the prior probability of a plus, class plus, is 7/12. The prior probability of minus then is left to be 5/12, okay? How we can calculate the class-conditional probabilities? Well, again, through maximum likelihood, okay? The probability of observing this particular pattern having the class plus is the probability of observing blue feature having the plus class multiplied by probability of observing a squared having this again plus class. And this is equal to 3/7 because we have 3 which are blue and are plus, and then we have 5/7 because we have 5 squares from the plus, right? We have a square here, we have a square here, here, and here, and here, right? So from 7 samples we have 5 which are squares. We multiply this and we come up with 0.31. The posterior probability of the same pattern being a minus is multiplied by the same way, and we have 3/5 multiplied by 3/5. Here we have a minus that's blue, here we have a minus that's blue, okay, and here we have a minus that's blue, which means 3/5. The same thing for square, and we have 0.36. And then in order to find, we said we don't need the evidence, right, because it's the same, it's just a scalar. Now we can find our posterior probabilities. We multiplied our 0.31, which is the class conditional probability, multiplied by the prior probability of plus, and we get 0.18. We do the same for the minus and we get 0.15. We said our classifier tries to maximize the posterior probability, or in other words, we just classified this particular sample, a blue square, as a class plus because its posterior probability is higher. And here is where I want to finish this little tutorial. I hope you got understanding of Bayes theorem and the Naive Bayes classifier. You can write me any comments there, ask me for anything. Subscribe for TensorFlow. Also look through my technology playlist, my machine learning different videos. I have explained linear regression, logistic regression, Fisher's linear discriminant analysis, and I'll do also more of these, so stay tuned. And also consider checking out my Patreon page, which is on patreon.com/TensorFlow, where you can find more content and also support the channel so I create more. I also put code from my past machine learning videos and any other stuff that you might want to check out on there, so you have access to this. See you next time.